when we talk about hemodynamics, what are we talking about? So hemodynamics is the assessment of fluid movements, and we can use fluid movements to do a lot of things. We can, as it relates to the heart, we can use the velocities in the chamber and the blood vessels to calculate pressure gradients, and as mentioned before, if there is a defect, such as a septal defect, or even across the valve, if there is any abnormal flow across the valve, we can determine the gradient, that is the pressure difference across the valve. And for shunts, we can determine the magnitude of the shunt, how significant a shunt is. So we talk about atrial septal defect and ventricular septal defect. We can assess the magnitude of the shunt, how significant the shunt is, by knowing a little bit about hemodynamics. And the normal working of the heart, we talk about the stroke volume and the cardiac output, cardiac index. We can use hemodynamics to determine the cardiac output and the stroke volume. Remember from your basic definition, the stroke volume is the volume of blood that the heart pumps out per beat. And then the cardiac output is the volume of blood that the heart pumps out per minute. So we can use hemodynamics to look at those things. And as a result, we can determine how well the heart is functioning. Okay? And as mentioned before, we can use it to calculate valve area. Okay? Because if we have a stenotic valve, say we have a aortic valve that's stenosed, that's narrowed, it's not opening properly, we can determine the severity of that restriction by just using hemodynamics. Even when we talk about regurgitation of blood flow across valves, so we talk about mitral regurgitation, we talk about aortic regurgitation, aortic insufficiency, we can determine the amount of blood that's going backwards. And as a result of that, we can determine the significant, how much regurgitation there is. Is it mild, moderate, or severe? So hemodynamics allows us to do that. And then another means of assessing the severity of regurgitation is something we call the regurgitant orifice area. And we're going to go into that in detail. That is basically the area through which the regurgitation is occurring. The bigger the area that the regurgitation is occurring, the more significant the regurgitation. And again, we can use hemodynamics to assess that. So hemodynamics is essentially one of the backbone of echo. Okay? So the first thing we're going to look at is the so-called Bernoulli equation. Okay? Because these equations help us to calculate gradients. So the Bernoulli equation look at the flow of fluid. We are talking about blood, but it look at the flow of fluid in a closed circuit. So the circuit has to be closed. And what you need to know is that if you have a closed circuit, so you have a pipe, the flow, as long as the pipe is not leaking, the flow at one point in the pipe is going to equal to the flow at another point in the pipe. The flow is going to be the same. As long as there is no leak or no siphon off, the fluid is not being siphoned off. The flow, just think about it, the flow is going to be the same all along the pipe. Even if the pipe has different area, cross-sectional area throughout the pipe, the flow is going to be the same. Okay? So that is one concept you have to try and get. Flow is going to be the same when you have a closed circuit. The pressures and the velocity at the different points is going to vary though. Okay, the pressure and the velocity at the different points are going to vary. And when we talk about pressure gradient, it is just the pressure difference. You know, if say you have a pipe and water is flowing in the pipe, you have to have something that's pushing the water. Okay, so the pressure at the initial portion of, say, the pipe have to be greater than the pressure at a more distal section in the pipe. If that's not the case, if you don't have that, if that's not happening, the water is not going to flow. Just think about it. The pressure have to be greater from where the water is coming from to where it's going. That's the water is not going to flow. And that is true for any type of fluid. If you don't have a motor or you don't have something that's, you know, if I mean, if you have a motor, then that's what the motor is doing. The motor is creating the pressure difference. Okay, so you have to have the pressure from where it's going to the pressure where the pressure where you start to the pressure where it's going. There have to be a difference in the pressure. The pressure initially, the pressure at the origin is going to be lower than the pressure. Sorry, the pressure at the beginning is going to be higher than the pressure at a more distal point. Okay, and the pressure difference is what we call the gradient. All right, so if you have a closed, so this is, look at this as a closed pipe, okay? And you have fluid flowing from P1 to P2. So what we know is that because the fluid is flowing in this direction, this pressure has to be greater than this pressure, okay? So P1 have to be greater than P2. So it's just all basic common sense, really. Because if P2 was greater than P1 or P2 is equal to P1, you're not going to have any movement of the fluid. Okay, so what the Bernoulli equation states is that this pressure difference, the gradient, this pressure difference we call the gradient, is equal to something we call convective acceleration plus flow acceleration plus viscous friction. So the Bernoulli equation, the original form of the Bernoulli equation is a long one. Okay, so the gradient or the pressure difference from point 1 to point 2, the pressure in point 1 have to be greater than pressure in point 2 for the fluid to flow in that direction. The pressure difference is called the gradient, and the gradient is equal to the convective acceleration, which is equal to half rho, the difference in velocity. So that is velocity at point 2 squared minus the velocity at point 1 squared. Because this pressure is greater than this pressure, the velocity at P2 have to be greater than the velocity at P1. Okay? Because the pressure P1 is greater than the pressure P2, the velocity at P2 have to be greater than the velocity at P1. So the convective acceleration is half rho, and rho is just the mass density, okay, into the square of the velocity at V2, right here, minus the square of the velocity at V1, right there. And then this is the flow acceleration. This is an integral sign, those of you who did math. So you're going to integrate, okay? And it's the velocity with respect to time. And then this is the distance, okay? And then the viscous friction is the resistance and the velocity, okay? So the gradient is convective acceleration, flow acceleration, and viscous friction. So P1 is the pressure at location 1, P2 the pressure at location 2, and again rho is the mass density of blood. V1 is the velocity, location 1, V2 is velocity at location 2. However, when we in clinical setting, both the flow acceleration and viscous friction can be ignored. So if you go back, so in clinical scenario, this flow acceleration and the viscous friction, you can just ignore those in clinical setting. So if you ignore those, all you're left with is half rho, which is the mass density, V2 squared minus V1 squared. So this is all you're left with. Okay? So this is what you're left with. The pressure gradient is equal to half rho velocity at 0.2 squared minus velocity at 0.1 squared. For blood, half rho is equal to 4. So you can replace all of this by the number 4 because for blood, half the mass density is 4. So simplifying the equation even more, the pressure gradient is equal to 4 into V2 squared minus V1 squared. And if we talk about, because we're looking into the blood vessels and stuff like that, for a very short segment, if you're talking about a very short segment, not a long tube, then you can essentially ignore V1, okay? The velocity at the initial point, you can ignore that for a short segment. So you can simplify the equation even more, that the pressure gradient is equal to, so this is a symbol we use for gradient, is equal to 4V squared, because if for a short segment, we can ignore V1. So this is what we call the modified Bernoulli equation, because it's coming all the way from the original Bernoulli equation, which says that the pressure gradient is equal to the convective acceleration plus the flow acceleration plus the viscous friction. For blood, flow acceleration, viscous friction can be ignored. So all we're left with is this. For blood, half rho, which is the mass density, is 4. And for a short segment of tubing, we can ignore V1. So we're left with the gradient is equal to 4V squared. And this is a very important formula in hemodynamics. Okay, so you have to remember that the gradient is equal to 4V squared. So let's look at some examples where we can use this. So let's look at tricuspid regurgitation. Okay, so again, we call this simplified formula the modified Bernoulli equation, which states that gradient is equal to 4V squared, where V is the velocity. If you look at tricuspid regurgitation, try to understand when we say you have tricuspid regurgitation, you have blood flowing in the opposite direction across the tricuspid valve. That is, in systole, blood is going to flow from the right ventricle across the tricuspid valve into the right atrium. That is what we call tricuspid regurgitation. In systole, blood is going to flow from the right ventricle across the tricuspid valve into the right atrium. For blood to flow in that direction, you should know that the pressure in the right ventricle have to be greater than the pressure in the right atrium, because we already established that principle that fluid is only going to flow from a high pressure area to a lower pressure area. So when you have tricuspid regurgitation, the pressure in the right ventricle is going to be greater than the pressure in the right atrium. Hence, in systole, blood is going to flow from the right ventricle into the right atrium. So that gradient, so remember we used this symbol as gradient. So the gradient across the tricuspid valve is the pressure in the right ventricle, which should be greater than the pressure in the right atrium. That pressure difference is called the gradient because blood is flowing from the right ventricle across the tricuspid valve into the right atrium. Okay? So what the modified Bernoulli equation tells you is that that pressure gradient is equal to the tricuspid regurgitation velocity squared. Okay? So that pressure gradient, difference between the right ventricular systolic pressure and the right atrial pressure, that pressure gradient is equal to the TR velocity, and you square it. That's what the modified Bernoulli equation tells us. TR velocity squared. Okay? So if you want to find the, say you want to find the right ventricular systolic pressure, then you just basically rearrange the equation. That's very basic math. Okay? That's very basic math because the gradient is equal to RV systolic pressure minus right atrial pressure. So if you want to get the right ventricular systolic pressure, you just move the right atrial pressure to the opposite side. And your right ventricular systolic pressure is now equal to the gradient plus the right atrial pressure. And again, the gradient is 4V squared. Okay. So I just showed you how to get the right ventricular systolic pressure. Another very important concept is that if you don't have any obstruction at the right ventricular flow tract or across the pulmonic valve, then your pulmonary artery systolic pressure is going to equal to the RV systolic pressure. As long as you don't have any obstruction at the right ventricular flow tract or across the pulmonic valve, that is a correct thing. So this is your short axis at the level of the aorta, and this is your cursor. If you remember your short axis, right ventricular flow tract is there, tricuspid valve is right there. This is the right atrium, and you put the cursor across the tricuspid valve. This is the TR, tricuspid regurgitation. Tricuspid regurgitation is a systolic flow. Your ECG is right there. Systole is from the onset of the QRS to the end of the T wave. So you have this spectral envelope, which represents tricuspid regurgitation. It is below the baseline because this is your transducer. With tricuspid regurgitation, the flow is from the right ventricle across the tricuspid valve into the right atrium. It's moving away from the transducer, hence it's going to be below the baseline. The gradient is equal to, you get the velocity, the peak velocity, which is 2.89. So when you square that, that's the gradient. So the gradient across this valve is 33.5 millimeters mercury. Remember, the gradient is the difference between the RV systolic pressure minus the right atrial pressure. That's the gradient, and it is equal to this. So if you want to calculate the RV systolic pressure, you just rearrange the equation, okay? You rearrange the equation because, as I showed you before, the RV systolic pressure, when you rearrange this equation, gradient is equal to RV systolic pressure minus right atrial pressure. Usually, this is what you don't know. So if you rearrange the equation, RV systolic pressure is equal to the gradient plus the right atrial pressure. I will show you in a later lecture how to get the right atrial pressure. So you can obtain this value, and you can get the gradient by squaring the TR velocity and multiplying it by 4, as we showed you with the modified Bernoulli equation. So you can get the RV systolic pressure. And again, the RV systolic pressure is the same thing as the pulmonary arterial systolic pressure, unless you have some obstruction at the right ventricular flow tract. So we're gonna stop here. You need to go over this lecture a million times until you fully understand it. And then on Saturday, we will pick up from where we left off. Okay?